In low-dimensional topology. Thank you.
So this will be just a summary of the mini tools which I gave already last week. So for all people who will read the sections that you will not start use for the rest, for me people, so I found this very nice topic which actually provide a complete algebraic description of some main objects of interest in low-dimensional topology, namely the category of n-dimensional quantiques for n equals 3 and 4. So let me recall you that this is a category where the objects are n-1 dimensional manifolds, and the morphism, say, M is a morphism and n-code from x1 and x2 to x2. So this is an n-dimensional manifold whose boundary is split in two parts. The first one is minus x1 and the second one is x1. And this is so the composition is given usually by knowing across the boundary, and the monoidal structure in the category is usually given by explaining. This is how we usually construct such category. And the main example of this is the category of the Hopf, where the only object, so the category is monoidally generated just by one circle, and the generated morphisms are they are functions one way or the other way from caps, and perhaps you will also need you will need to be able to switch to trans. And as you also all very good know, this category is so if you just restrict to the spine of this object, so that you will get such graphs here, and actually, so the relation is just associativity. For associativity, unit axiom or unit axiom, so you can hold both these things one way or the other. And the only one interesting relation is the Frobenius relation, like this is. It's about compatibility of multiplication, multiplication. So on the other hand, so a vector field together with commutative multiplication per unit such that this relation is satisfied. It's called the Frobenius algebra. And putting all this together, you will obtain the theorem, kind of your theorem that this Hopf is a monoidal category. It's a monoidal category clearly generated by its Frobenius algebra object, which is just one into. So, needless to say that this is complete understanding of the category in this way provides a classification of TQFTs in the way that basically every function from the Hopf to some linear category, let's put it today, is actually completely determined by the image of the S1, and this image needs to be a commutative commutative. You have also relations with the function, and it's okay. So therefore, this description, this is basically shows that we understand everything about the algebra. And the aim of this talk will be to provide similar statement in the case n equals 3. So our aim today will be to analyze this for 3-dimensional and 4-dimensional categories. So I will completely describe you this topological side. So let us start from the algebraic side. So on the algebraic side, the idea of the notation here is to exchange Frobenius with Hopf. And remember what is Hopf algebra? This is just an algebra. So it is directly based with the multiplication, multiplication, unit, and co-unit, and also one additional invertible and amortizable H, which is called n-cobordisms. And so I will use the same graphical notation for multiplication, unit, or unit, and this will be plus for the antipode and minus for the inverse of the antipode. And now, so the generalization is not yet done just by replacing Frobenius algebra by Hopf algebra. By the way, so in the whole talk, Hopf algebra will be for finite dimension. And so actually, what I will need is Hopf algebra object in some braided monoidal category. Okay, and so if you remember the relation which this morphism have to satisfy in the Hopf algebra, then you probably know that this two morphism should be bi-algebra, bi-algebra, and this means that so except this associativity, unity, co-unity axiom, we will also have a bi-algebra axiom which tells you these axioms. And the only difference, so if you would like to consider this H here, so now this H, so I'm breaking another, so let us do this for my category C. So now my H will be not just a vector space, it will be just on there. But now, so given an object with a C, I will require that this object has a morphism M from tensor power of H, second tensor power to H itself, from H to H its second tensor power, and so on. So all this morphism. And the only difference, the only difference in the relation which I will require for this Hopf algebra object in braided monoidal category is that now you know that this category has a braiding. So I can always braid any object. So I have morphism, I can change either this way or the other way. And so here, to exchange these two guys, I will use this braiding and not commutation anymore as in vector space. And so in this way, you will obtain a Hopf algebra object in braided monoidal category. So it's actually sometimes it's also called braided Hopf algebra object in braided monoidal category. So I will go back to the braided Hopf algebra object. Okay. Now, next question: do we have interesting examples of such braided Hopf algebra object? And indeed, we do. So one very interesting example is if we consider the category of three-dimensional coordinates, and these are connected, oriented, compact, three-dimensional coordinates with connected 100. So it's not the most usual case, but it's a huge piece of the category I mentioned before. So therefore, I'm not even putting here. So sometimes people put in criteria of 0, but I will just only work with this category of three-dimensional coordinates to say origin. So I'm not allowing disconnect boundaries. And also, I will deform a little bit the monoidal structure of the category. So let me define also same. So the object will be just a disk. This three-dimensional one handles attached, two-dimensional one handles attached. So this is the surface of genus G, which I'll denote G, but it's not a closed surface, but it has one function, so it has a boundary. And I will represent this boundary by this square. And you can clearly identify all these objects just with numbers G, with, as I said, just natural numbers. Okay. Then morphism from one such surface to another such surface. So let me, for example, go again such surface, and this is an object which I'll call 2, and I would like to go to an object which I'll call 1, and for this I will just draw such a view. And now to represent the surface which I so here the bottom surface. So it's need to have an opposite orientation with respect to this one. And I would like to represent it by just drawing, for example, this line, and think about this line as actually it shows the one handle attached to this bottom square. So you just remove. So you think about providing a hole. So you remove the tubular neighborhood of this line, which provides you a genus one boundary component downstairs. So this will represent more to be 1. It's clear how I think about this picture as a morphism. Okay. Then also composition in this category is a little bit different. So for example, if I would like to compose this morphism, so now I am stopping to draw three-dimensional picture because it's too complicated, and I will draw just one-dimensional picture. So here this line goes twice. This. So it's like curl and going down. So this is a morphism from 1 to 1. And I would like to compose. So this 2 to 1 should be composable with 1 to 1. And I need to obtain a morphism from. And this morphism is obtained in the following way. Here, so it should be, so as I said, for morphism, the composition should be given by gluing along the boundary. Now the downstairs boundary of this guy is just a surface. So it's just this tubular neighborhood of this guy is a one handle which goes along this red line. And now I should compose it with this guy, where I just cut this one handle and embed it along this guy. So this is the structure. So you just cut like this, embed here along this guy, and what you see is now you will have the same line as before, but because in this handle you have 2 copies of this red line, so you will also obtain 2 copies of this line here. Okay, and then so after this you just do whatever is done in this tunnel, and this tunnel it's composed as this one with this one, it goes this one, it goes down, and this one goes. No, there's another. Okay, hope this one sounds clear. Okay, so this is a composition category. And now about monoidal structures. So this is all the modified. So monoidal structure is given just by viewing side by side this guy. So for example, I can also put here instead of what I computed for the moment before the composition, but I can also compute here and then the product. And this will be just stacking these 2 cubes side by side. Okay. This has the advantage compared to the disjoint union. So if I will consider, if I allow now here disconnected boundary, then my category will have infinitely many objects. I will not be able to compare object of genus 1 with object of genus 2. So they will be all, so that it will be infinitely many generators in category. What I would like is to provide some similar description of SQL as I have here for the tuple. So I would like to have it as a monoidal category really generated by just one object. And you probably can already think that this object will be raised for algebra. Okay, So therefore, I cannot. So therefore, this structure is exactly what is needed in order to the whole category will be generated monoidally by this F1. Okay. So this is and topologically there is no problem absolutely. So I mean, I'm just so instead of the whole category with all the connected boundary, I consider only some piece, but actually it's detects almost all topological information. There is no problem. Okay, and now so this is a monoidal category. So okay, let me so it's basically just putting side by side the thing. So this is one guy, two guys, so this sense you. So basically F1 tensor F2 is equal to F3. Okay, and now this is not only categories is equal, but I would like also to consider this as a braided monoidal category, and the braiding will be given by the pooling guy, where you just braid one handles. So now we have a braided monoidal category, and now I promise you that I will give you an example here of this braided algebra object. And indeed, so the claim is, and this is claimed, this was discovered probably by Crane and Yetter, also Kerala. So there are many people, Lubashenko, Kerala, and Euro, who were working on with this category. And all these people observe this nice fact that this F1 is a braided algebra object in 3 folds. So this is a nice example, non-trivial example of braided algebra object. And in order to say, so we need to describe the structure morphism. And indeed, the morphism I just gave you here, it's a multiplication. So this one is a multiplication, one is a commutification. Commutification should go from 1 to 2. And so I should mention that I'm in this picture, I'm looking at the morphism from bottom to top. And in the algebra, I'm reading this graph from, sorry, I'm reading here from bottom to top, and here I'm reading from top to bottom. Yeah, there. This is by historical reading, so to confuse you completely. Otherwise, so just look at our paper. It's another motivation to look at our paper, where instead of this so-called bottom tangles in handle bodies, because the top tangles, you just need to put a horizontal line to mirror image there. Okay. Then eta is the guy who's says. So this is the morphism from 0 to 1. Epsilon is the morphism from 1 to 0, which is like this. So if you apply epsilon to any morphism, before what it does, so if you have here something, this epsilon just kills this line. So just remove it from there. Then we need S, which is from 1 to 1, and we need S minus 1. Which is again from 1 to 1. And so let me pull this so which is very bad. I lose my book. So these are the S and this minus 1. And so basically it's a nice exercise to check that all topological relation are satisfied by the triangle. So it's really an exercise how did you understand this composition? But it's really not hard and even fun. Okay. Now let me give you the following definition. So assume C is a braided monoidal category. Then an object in this category, which is actually a braided algebra object, H in the C is called a hero's Hopf. It comes equipped. So already it's a braided Hopf algebra. This means it already has associativity, so it has all these morphisms, it has antipode, and it satisfies all the relation, including this one. Okay, and now I'm looking for some more structure, because you see the motivation is this 3 code will not be yet generated by this F1. Just because all quantiques we have seen so far, we can embed them into a suite. Because it's, you see, it's just a cube with our cube inside removed, and so it's perfectly embeddable into a suite. What is lacking to obtain any three-dimensional manifold is to have closed component which would be interpreted as arbitrary components on to provide any three-dimensional manifold. So therefore, this is what I'm going to add now. So this Habiro algebra. So it's comes with the first of all with the even element. So we can convert one sample element, which so don't confuse this with the antipode. So this is just goes from 1 to h, and the antipode goes from h to h. So therefore, what can distribution minus would mean the inverse even element. So this is a Hopf-even. And then we need Hopf plane from h10 to h1. So which are denoted like this. And the Hopf plane sigma bar which goes from 1 to h10 to h, which are denoted. And it's satisfying bunch of axioms. So if you would like to look at all axioms, you can either look my mini course I gave last week, so you probably have in your emails links, or you look at the Atelier paper where all of them are also. Let me just give you a flavor of how it looks like. For example, this should be Hopf pairing. So then it should interchange multiplication for multiplication this way. Then pairing and co-pairing should be a dual to each other in the sense that say the exact relationship is satisfied. Then I mean there are a bunch of axioms about even basically saying that it's complex multiplication, just several elements. And probably the most important one is it's about this is about so-called adjoint action. So the adjoint action, which I do like this. This means that you co-multiply here, you take your strand, you put here S, and you do like this. So basically you just co-multiply this X and X with H1 and S of H2 on your elements. It's exactly the adjoint action. And these adjoint actions, I think this was observation by Maggi. If the adjoint action satisfies this axiom, then all structure morphisms listed here commute with adjoint action. So this is why. So this is kind of very important property. So there are other axioms. I'm working on how to read them. Say you will find them in literature. So there is no problem with this. And then so the next thing which I'll introduce is the following one, K. Okay, I did a mistake. It was not very smart to start with this board because you will not see it here, but hopefully we will still manage somehow.
You could use the button on the left.
Huh?
You could just use the button on the left.
No, but I would like to keep some for a while. So yeah, so it's fine. I will just go a bit more if I need. So we introduce this combinatorial algebra, and then let 3 be braided monoidal category, really generated by Habiro of algebra object. Okay, this is called algebra object. I will call HB. Okay, And now there's a screen, or first it was conjecture. The conjecture, and this was first formulated, this conjecture by Keller in the 90s. So basically, it's him who started this algebraization program of four-dimensional topology. So what he was looking for some algebraic presentation of this category of three-dimensional forms, and he postulated some axioms. So some of them are indeed in the definition of the Habiro of algebra. However, I use the word Habiro because it was Habiro who completed the axioms, but Habiro never published. So he gave some course, I think, in the beginning of 2000 in Paris, but he never published anything on this topic. And it was Atelier who claimed Habiro as a proof of the following fact, that 3-4 is actually equivalent to this real. So this means that we have a complete presentation of the categories given of the model by some Habiro topology. Yeah. But there were no, so basically there is, until now, there's no proof in the literature of this fact. And so Asaida just started, so just say that Habiro has a proof, but so I mean it's already 22 years. So the proof was not published. And so what I will do here, I will so so I hope soon it will be appear on the archive, but we have a series actually, and this is by so it's a collaboration with Ivelina Bobtcheva, Marco De Vinci, and Riccardo Piergallini, and it's basically says that the functor y from 3 alpha to 3 over, which says clearly here this Habiro algebra object is sent to this F1. So this is an equivalent of categories. Okay. And then we also describe how this functor. So in order to describe the functor, I need to say where the generators are going. So we already know that where the algebra. So like the multiplication, because this H is a range of algebra objects, the multiplication is goes to this one, before multiplication goes to this, and blah blah blah. So this we already have. And we just need to say here because this Habiro of algebra has additional generators, which is ribbon element and pairing and co-pairing. I just need to tell you where I send this guy. And I will tell you in a sec where I send it.
Isn't it equivalent of braided monotype? Isn't it equivalent of braided?
Yes, it's equivalent of braid like this. Braid monotype. Yeah. Yeah. So sigma goes to the guy who looks like this. So and this is actually so it's a whole pairing, so it should be both thing and indeed it's a different thing. So remember sigma is morphism from 2 to 0. Then sigma bar, it's a morphism from 0 to 2, which looks like this. It's again a thing. As a twist, so the ribbon element, they're going so far goes to this guy, and -1 goes. Okay, and so the question is, how would you like to prove such a theorem? And actually, our proof goes through kind of a completely different theorem. So this is just a small outline of the actual theorem. Yeah.
Sorry, I'm having trouble understanding the picture for sigma. Are you showing those red circle? Or is this a center picture?
Exactly. This is the Atelier picture. This is exactly. This is the new element. This is the Atelier.
Okay, and then I just take like Blackboard framing.
Blackboard framing, exactly. Blackboard framing, essentially. Yeah. Yeah. Exactly. Yeah. Okay. Sorry for not mentioning this. Okay, and so the main theorem which I will prove today, and this is the theorem was actually proved by Bobtcheva and Piergallini around 2012. So this is an issue. So this is 230-page paper by this device where they prove they develop the whole formally dimensional. And we just will publish soon, like so I hope it will be 23 or beginning of 23. And we just reduce this group of 230 pages to like 60 pages. And this is because they actually okay, let me first perhaps tell you what is a theorem. So there is some cobordism category in dimension 4, which I'll call 4HB, is so-called 4-dimensional two-handed bodies. And I claim that there is an algebraic presentation of this category by Hopf, which is actually also a braided monoidal category generated by so-called Bobtcheva Piergallini for algebras. Okay. And then from this guy, so you can just take a boundary factor from these handed bodies and go to the sequel, as well as here you can take a quotient by 2 additional relation and you go to the C-alg, and this equivalence will produce this equivalence here. So this is the strategy how you prove this presentation theory. So you actually proving something much more general about 4-dimensional cobordism, and just as a corollary of this, you get this theorem. So up to some details, because you will see. So our algebra for alg, it will be a little bit different presented. So we will have, instead of this bi-pairing, co-pairing, we will have integral, co-integral, but basically we have a complete translation of how to represent these guys. So how to go from integral to integral, pairing, co-pairing, and factors. So therefore, let me now explain you who are actually this category and this category, and then to discuss a little bit first of what are the results, so what they provide for us. So 4HB is a category of 4-dimensional two-handed bodies. So who is a 2-dimensional handed body? So to construct this handed body, I will always start with a 4-dimensional wall E4, and this will be like 0 level in my compression, and then I will attach 3 4-dimensional one handles. And then the second level integration will be X2, where I will attach to this X1, which is 4-dimensional one handle body, attach 2-dimensional 4-handle. Whereas this HI4, it's DI times D4 minus I. So for example, H14, it's D1 times D3. Okay, to attach one handle, you take your D4, which has a boundary S3, and you remove 3 balls, and you attach one handle like this. And then to do a 2 handle, what you're doing, you do attaching sphere. And this is a curve on the boundary of H1, on the boundary of the H1, which is also always framed. And so I always prove this Blackboard framing. It can be noted. And so if I have here, for example, another one handle, then there could be another curve going, for example, also in this handle, linked with this one, going like this. So basically you have a closed curve for every two handles and such one. So because you would like to represent these things by planar pictures, by planar diagrams, usual, what you're doing instead of this one handle, basically the whole information about this one handle, just you need to know whether this curve goes to one handle or does not. And to indicate this, you are putting so-called dotted components. So you're putting here small meridians on these one handles with dots on them. And then you just project them down to 3, and this is a so-called Kirby diagram of this four-dimensional two-handed body. So this is the Kirby diagram. So let me provide you a few examples of such a diagram. So for example, CP2 will be presented just by, this is the Kirby diagram. Okay, S2 times D2 will be presented. So this means that you have D4, you don't attach any one handles, you just attach two handles along this curve. And I'm not attaching never 3 and 4 handles. So therefore, this is actually not CP2 versus CP2 without the component. Okay, and this S2 times D2, this is again, there is no 2 handles, only 2. There is no one handles and only two handles. So this is a Kirby diagram. And in general, you will have something so like no component is then two handles, which can be answered. So these meridians. So just unknown bounding disk. This dotted just staying with one. So this is how you represent this four-dimensional two-handed bodies, and consider like two such Kirby diagram, which I'm drawing in blue, are two equivalent. So you consider them to be equivalent if they can be related by isomorphism of attached maps. So this means just planar isomorphism of these two handles. Then handle slides of two handles over two handles. And the third one is creation and removal of one handle makers. And so topologically, this means it works. So like isotopes, it's just we always consider the diagram up to isotopes which are generated by randomized moves and planar isotopes. So this is not a problem. So handle slides means that if you have one blue component which may be not and linked with the other one, and another component which again can be not fluid, then you can replace this by handle slide. So you take this component, so the first one, and you connect it. So just by a copy, because it's a plane component, it has a normal vector. So you just the endpoint of normal vector. This will define your second component like this. So this is the handle slide, the two handles over the other two handles. And so this is the move number 2, and move number 3 allows you to remove each time if you have something like this. It allows you to remove it. So this is 3, and this is 2. And 1 is just randomized rules. So basically, I can represent morphisms in my category for HB by looking at such group diagrams modulo these two moves. So you, for example, this is probably the people worked already with the 3 corpses. This looks like Kirby 1 move, and instead of it's Kirby 2 sliding, probably Kirby 2 is sliding, and this looks like stabilization move, which replaces 4D there, so Kirby 1. Okay. And now, so I could organize. into a category by looking at three-dimensional one-handed this object and four-dimensional two-handed this more. So what is important here is that I don't consider any 3 and 4 handles. So this means that the set of equivalence relation I put here. So I also call it two equivalent. So I didn't say that the corresponding bodies are diffeomorphic. So this relation is actually weaker than the diffeomorphism, because so in the sense that in order to generate any diffeomorphism here between two such presentations, we will also need to add creation and removal of 2 and 3 handle. And this is what I do not consider. And the question whether the set of these two equivalences is actually a real proper subset of diffeomorphisms, it's an open problem. And this problem, so the people think that it should not be, so it should be a really proper subset, but there is no invariance, so it was. So far, there were no invariants after two equivalents, but only after diffeomorphism. So therefore, the people didn't consider this. So I mean, there were no tools to study this relation. However, this problem is very closely related to the so-called Andrew-Curtis conjecture in combinatorial. So there you also you have a balanced presentation of a trivial group, and you would like to know whether you can reduce it to the trivial presentation by some set of moves which do not admit stability, so changing the number of the relation. So therefore, this is something very similar here. And so like if you would like to show that this set is really a proper subset, that there exists diffeomorphic handled body which are not equivalent, this would be this would solve this long time staying problem in four-dimensional topology. Okay, so I hope I described a little bit. So if you have, or if you would like to see more details about this four-dimensional morphism, so I can provide at some point. Later we can discuss in private. But what I would like to describe now is the algebraic side of the equivalence. So again, let's see the braided monoidal categories around tensor units, so braided monoidal. Then braided Hopf algebra object H in C is Bobtcheva Piergallini Hopf algebra. Again, if it comes equipped with an integral, which is morphism from H to 1, and which I'll draw like this. This is my integral. Then the co-integral, it should be a big number from 1 to H. So it's an element of the algebra. Like this. Then this morphism, so this is or even endomorphism, which are right once minus H to H. I'll simplify just 5 plus or minus 1, and then the whole variant is in the setting one can define already from the existing structure as you take 1. So you take the even element here, and you co-multiply this, and then you correct it by -1, -1, and you put here x. That is a defined group of variant. Okay, so this is basically this is I don't need to require this as a new morphism. And now let me give you the axiom. So for the integral, basically you have the standard axiom. So if you apply here for integral, then you have this, or you have you ask this property, then you ask, and then you ask that actually your integral to integral they compute this test. And the same. So these are a bunch of axioms, and there's so these are integral to integral axiom. Then you have Riven axioms, basically. So this is what I didn't draw in the reduce, just so you have n and m here. So this is the same as n plus m. Then again, Riven stays invariant under S. Also, it's completely epsilon, and it's set of elements that I can push it out to so then we need the whole pairing axiom, which I already do. So in this way, and now you have so the last set of axiom. It's so-called Bobtcheva axioms, which I really learned from them. So these are two axioms, two additional axioms, which look like this. So if you the first tells you how Riven element propagate through the multiplication. And this is given by the following. So if you put here this guy, you put here, and here you put minus one. So this is the first axiom. And the second one express you the positive gradient, so it's negative gradient and Hopf. So this is the positive gradient, and you can express through the negative gradient in Hopf. S and here. So this is another, and here so this is so basically this is the algebra. So this is the reason why I'm giving this talk here, because I would like to sell you this great algebra, because this algebra knows everything about four-dimensional two-handed bodies. And basically, so if you think, for example, if you don't like this approach about this equivalent, that you can just think that the other complements, the union of 3 and 4 handles, it's again a four-dimensional three-handed by conjecture. So say for you understand, like you understand half of the four-dimensional topology, you can understand this algebra. And there are examples of this also. So first of all, so let me tell you that you know already a lot of examples of this algebra. For example, this algebra is Gisborne. This algebra is Gisborne, without using the structure.
Anna, you're already a few minutes over time.
Oh, okay. Okay, then let me just tell you that if you have H to be finite dimensional unimodular even for algebra, then this space H together with a German representation where the action looks like this. X is H2. Then this is Bobtcheva Piergallini of algebra in H mod. So this means that you know already a lot of examples where of this algebra. But somehow, so the main message which I wanted to make here is, as long as this Riven algebra is factorizable, what happens is that the corresponding invariant sees just this three-dimensional boundary. So if you would like to say something about four-dimensional topology, then your H should not be not factorizable and not semi-simple. And also of these guys, we have examples. So for example, if QSO2 at the root of unity R, so whose order is 0 and 4, it's an example of a non-factorizable non-semi-simple. But the problem with this example is that actually this guy sits in a bigger so-called restricted SL2, and this sits just at degree 0 part in some bigger which is factorizable. And this is not good enough to see something four-dimensional. It just sees three-dimensional boundary and the spin structure and nothing else. So therefore, or we have cohomology classes. So therefore, so I'm really would be very happy to discuss with everybody in the audience about the example of non-factorizable nonsense of algebras, which are really kind of far of being factorizable. So really far of being factorizable. So this means that like Greenfield double, it's something which is essentially three-dimensional. So at the moment you produce your gradient by Greenfield double, it's not what which will see four-dimensional even. So this is all what I want to say.
Thank you very much. We have time for some questions, please.
You're looking for them over the complex numbers, right? Or are you okay with different characteristics?
I'm okay with the characteristics. So there are some negative results about final characteristics by Ivelina Bobtcheva, but perhaps yeah. So I'm open to this. Yeah.
And the base, like the braided category which it leads, do you want that to be something like non-degenerate or degenerate? So you're looking for a non-factorizable algebra in braided category, which should be
which should be so it should be the Bobtcheva than
no, but the category itself could it be like non-degenerate, you expect that to be something in particular?
No, it's exactly it should be non-degenerate. So it should be degenerate. Essentially degenerate.
No, but the category itself. So the braided category which it leaves.
So I don't know what does it mean for category itself to be degenerate. So, but the braiding should be degenerate. So in the sense that this monodromy should be essentially degenerate.
Okay.
I think the question where you follow the leaves. I think in your example is better.
Yeah, that's something that you
So this is so here it's H more, but I can ask yeah, but you can here is H more here. But you can take instead of H more, you can take any unimodular even category and then it will be instead this, it will be and you take a set of adjoint representation and it will be again which family of example. Again, yeah.
Okay, if there are no more questions, let's thank Anna again.